All right, ladies and gentlemen, welcome back. We have just gotten done with L'Hopital's rules, a really nice break from all the other intense limit stuff that we are doing. Today, we're going to nail down some of the examples, all right? So it's really, really simple. Just to give you a quick recap, let's jump right in. The quick review was this, and I'm going to try to dictate this a little bit. This is what we normally used to do. We started with always taking the limit. It either led us on the path of being done altogether, right, because it was just like a number, or you lead to the form of the indeterminate, which is one of these four guys. If it's so, then you had to simplify, and once you simplified, you'd go back and take the limit again. And it could lead you back to the indeterminate form, and you keep going down the rabbit hole, but ideally, you'll simplify it enough or put into the right form, so when you take the limit, you could reveal what the limit actually will be. And sometimes the answer to that is does not exist, which is perfectly fine. When we were tackling stuff last video, we talked about that infinity over infinity and 0 and 0, those two particular indeterminate forms, right, we could leverage derivatives by using L'Hopital's rule, right, which is a quicker way. Quicker is subjective, but it's a quicker way if you're good with your derivatives to get to that place where you can take the limit again. And it's all based off looking at the rates of change. All right, so let's jump right in, okay? And I'm going to try to do my best to have enough room on the screen, all right? So we don't know much about trig functions, but I do think this is all the same, all right? So here we go. So whoops, I forgot to not press buttons. Got big old fingers, guys. All right, so as x goes to 0, well, what does sine of x plus x squared minus x all over cosine of x minus 1, what does that go to? Well, let's see here. In the numerator, cosine of 0 is 0. 0 in x squared minus x, so all this crap up top is effectively going to 0. And in the denominator, cosine of 0 is 1. And then 1 minus 1 thus gives us 0. Again, this is just basic trig stuff, and that's what we end up with, all right? So 0 over 0, which is the indeterminate form. Now, we talked about this. All you got to do is take the derivative. So we're going to L'Hopital this guy, and then if you know your derivatives, you're good. Otherwise, you need to do some algebra. And this is kind of where it's superior. You're not really going to understand the algebra behind sine until you get to Calc 2, which is when you talk about expandable sequences and series, and that's when we start talking about the true definition of sine and cosine. So using L'Hopital's rule allows us to access answers to problems that normally are not reachable for us, all right? So we're just going to take the derivative now. Getting back to the problem, take the derivative of the top and the bottom. So the derivative of sine x plus x squared minus x over cosine of x minus 1. I'm just going to take the derivative of the top and the derivative of the bottom separately. Again, this is about chasing down the rate of change. Once you do that, that would be equal to cosine of x plus 2x plus 1. In the denominator, we end up getting a negative sine of x. And then straight up that, because the derivative of 1 is 0. All right? So now, let's take this guy again. So as x goes to 0, cosine of x, again, this is just me showing all the necessary work. What ends up happening? Well, let's see here. As we approach 0, well, we just said sine of 0 is 0. So the denominator is 0, but we're not done yet. Why are we not done yet? Because when we plug in 0, that doesn't guarantee us anything because the numerator could be a number. Remember, it only works on 0 over 0, infinity over infinity. All right, so when you take this guy, well, the cosine piece, well, that effectively go to 1. So that's going to be 1-ish plus 0 plus 1-ish, which that means this is 2 over 0, which means a really 0, which means it's a set number divided by a really tiny number. So we know this is going to be some form of infinity. Don't know which one, plus or minus. If I needed to, I needed to approach 0 on both sides. But bottom line is, this is enough for me to say, well, therefore, and this is me being lazy, guys, this would have to go to infinity of some sort. Well, not infinity. We'd have to check the limit from the left and right. But bottom line is, we know that this thing, well, actually, that's what we'll have to do. If you take the limit as x approaches 0 from the left, you start to see that it is going to go to positive infinity. This ends up being positive. And this thing also ends up being positive. But pause for a second. The sign, since it's negative signs here, for you guys who don't remember your trig, okay, sign as you approach 0 from the negative side is going to be a negative number. So that means one's going to be going to negative infinity, the other one's going to be positive infinity. So therefore, the overall limit do not exist. So all the limit stuff that we did, the piecewise stuff, and I'm not going to stress you guys out by showing all the work. But bottom line is, once you got here, you should have split it, since you got 2 over 0, into taking the limit from the left and the limit from the right. And that is extremely important to see if the limit exists or not, because after all, they are asking us to figure out the whole limit. Now, if this was a piecewise, then we'd be good to go. Only one side to check, and save us quite a bit of time. But the moral of the story is, we check both of these. One goes to negative infinity, the other one goes to positive infinity, and thus, that's the justification behind it not existing. So let me not shortchange you on the explanation. All right, let's move on. But bottom line is, L'Hopital's rule. Derivative top, derivative bottom, take the limit again. Done. All right, but that's only for a 0 over 0, infinity over infinity. So here's a question for you. What about when I have a function like this? Can I use L'Hopital's rule on this? Well, let's see here. If I take the limit, so I'm just going to go at it as it is, the limit as x approaches infinity. I told myself I was going to work on my handwriting. So that's what I'm going to do. As we go to infinity, well, that x is going to blow up, so it's effectively big. And then e to the negative x is going to be, well, let's see here. E to the negative x is really 1 over, so that's effectively going to 0. Oh, so that is an indeterminate form. But this is not one that could be used with L'Hopital. So what do we need to do? You got to write some algebra. So check this out. I'm actually going to see this negative exponent, so this is the intuition. So let's just do some quick rewrite simplification stuff. And what I'm going to do is I'm going to rewrite it in such a way that I can take the limit again, like we always do. But watch what I do here. So this, I'm just going to use the fact that I know that negative exponents are 1 over. Okay? Now, I'm going to take the limit again. So as x approaches infinity, x over e to the x, well, that'll blow up, and that'll blow up. Oh, look, it's infinity over infinity, big stuff, right? No big deal, though, because we can now use L'Hopital's rule. So I'm going to L'Hopital it, even though it's not even his rule. He's just a rich Frenchman, all right? And again, we're taking a derivative of the guy, the place that we rewrote the function last. Derivative of this would be 1. Derivative of this would be e to the x. So finally, when I take the limit as x approaches infinity of x over e to the x, simplified version, 1 over e to the x, then I end up getting effectively 1 over something really big, which 1 over really big implies that that's going to be equal to 0. So therefore, the limit as x approaches infinity of x e to the negative x equals 0. Now, you're probably going to say to yourself, well, Rush, could I do this with using the old stuff, the old algebraic stuff, right? Just simplify it in some kind of form. Some functions you guys don't have enough accessibility to. You don't know a great deal about sine, cosine, and e to the x. Like, what they haven't taught you yet is that e to the x is really that form, and that thing is really cosine x plus I sine x. So there's a bigger story behind e to the x and its relationship between cosine and sine. Cosine and sine are frequencies. E to the x is called a natural number because it's naturally occurring in nature. So therefore, there's a gigantic relationship here. But you guys don't know enough math yet. You haven't seen this yet. You get a little bit into that in Calc 3. So we're giving you the tools to get where you need to go. So moral of the story, L'Hopital, infinity over infinity, and a 0 over 0. You still might need to use algebra. You're not totally off the hook, but it's important. All right, let's move to the next example. Okay, so this is actually a really, really cool example. Why? Because it's exactly the same as what we're used to. So as x approaches infinity, we're going to jump right in. E to the x minus 3x cubed. Well, that goes to big old number minus big old number. Again, indeterminate form, right? So you're like, oh my goodness, well, what is the big deal here? Well, what we normally do in the beginning. Now, why can't I leverage L'Hopital's rule? infinity minus infinity. Now, if it was written as something divided by something, like 0 over 0 or infinity over infinity, then we're really ready to rock and roll. So we're just going to do some simplification here because that's my only option. I'm thinking that I'm going to force factor e to the x out of everything. Why? Because it's the biggest growing function, and this is some cool Calc 2 stuff, and that is that functions itself, just like numbers have orders, functions have orders. I could tell you which function is going to grow faster than other functions. That's to come in Calc 2, right? So they are kind of like numbers in themselves. All right, so I force factor it out. Now let's take the limit again. So as x approaches infinity, we get a big old number times 1 minus, well, let's see. Well, this right here gives us the infinity over the infinity part, right? So that's a big old issue. So this is the issue here, is what's happening here. So I'm going to zoom in right to this point, and I want to examine what's going on here. So everything in yellow is going to talk just about there. So let's look at just there. And we're going to infinity, so sidebar. As x goes to infinity, what happens to 3x cubed over e to the x? Well, that goes to infinity, and that goes to infinity. So the best bet is we just need to do the differentiation from the top and the bottom because we're going to use L'Hopital's rule just on this. We're taking just the limit of this in particular piece. We're not using the entire function because clearly that thing altogether is not going to be infinity times or divided by infinity or 0 divided by 0. So remember, L'Hopital's rule. So I'm going to take the derivative of the top, which is 9x squared over e to the x. Take the limit again. That thing goes to infinity over infinity. But what do you notice? The top went down 1 degree. So I have this theory in my head that if I keep going, eventually it will terminate. So let's try it again. So now going from here, if I do 18x over e to the x, well, that goes to infinity again. And this goes to infinity again. And I can keep using L'Hopital's rule over and over and over and over until it gets me where I go. So if you notice, the top is shrinking. This gives me a constant finally. And this gives me e to the x. So what did basically happen here? Whoops, sorry guys. Discard. What basically happened here is my entire slideshow decided it wanted to be normal. So, all because I bumped into stuff. All right. So, taking it back to where we were, which I'm gonna go ahead and do a quick rewrite of this as. Wow, Sway, wow.